And now we move on. Next thing we're going to cover is something called a binary tree. When we left off in the last class, we had just talked about doubly linked lists, and we were talking about a node. We created a struct, and it had a data value, and then it had a pointer to prev and a pointer to next. Well, we're going to steal that idea. And again, this is the whole approach that I like when I'm teaching this class. We're going to steal that idea because now we're going to come up with a node, and we're going to start with a node, but instead of calling these pointers prev and next in our struct, we can call them something a little more appropriate, like maybe left and right, a pointer to the left and a pointer to the right. So just by taking a look at this binary tree that you see right now, it's set up instead of horizontally, we start moving vertically. So just a little quick item, when we used to search, we did either linear searches or we had learned the binary search. Well, this search is going to be a little bit different. This one, and again, is sort of like the binary search if you start looking at big O notation, which we didn't talk about yet. But we have some sort of, yeah, I can search a binary tree quick if this is set up the way we like it. And we'll talk about the setup and everything, but I can get somewhere pretty quick. So starting out with some of the notes I put up above, it's a non-linear structure. You know, instead of all horizontal, we're now able to go different directions, and we're going to see all kinds of moving around. When we take a look at this, every node has 2 pointers. The pointers can either go to 2 nodes or they can go to null values. So back when we were doing linked list and doubly linked list, we didn't have so much null going on as we do in something that looks like this. Okay, what else do we have? Every node has a single predecessor, which we're going to call parent, and has 2 children. And that's for a binary tree. Later, we're going to look at structs that might have 3 data values and 4 pointers coming out of them. But for now, when we're doing 2, we're sticking with the term binary tree. Again, I mentioned we have left child and right child. So some terminology. Nodes. We have a giant tree. We have a subtree. Instead of header or front, we call this pointer to get us started root. And why? Well, if you take this bad boy and you flip it upside down, it's supposed to look like a tree. And what's at the top of trees? What would be at the end of each one of these, like branches? What do we have?
Leaves.
Leaves. Okay, so these are going to be called leaves later on. And this is the reason why we call this the root down here. So it's trying to make sense of the terminology. Again, the root, left child, right child. We only have 1 parent. We have subtrees. We have all kind of stuff going on. So I'm going to start, and we're going to build what's called a binary search tree, which means we're going to build a tree. It's going to look like this, but when we build it, we're going to build it in a way that it makes sense for us to be able to search. Okay, so I'm going to get ready, and I'm going to build this tree, and I'm going to build it with the letters M, F, R, P, and B. So I take a look at M, and that's going to be my first node. My root would end up pointing to that. Now, we're going to make these so that they're set up alphabetically. So I take a look at the next character. It's an F. And where would that go considering the M? Well, what I mean by that is it less than or is it greater than? Glad you made it, Yug. F is less than, right? So I'm going to make a node that's going to go out of M to F. My next character is R. I know R is bigger than M, so it's going to go to the right. My next character is P. By the way, I did have a student one time who printed out the alphabet because it made it easier for him to not have to run through every time. But yeah, P is greater than M, so it's going to go to the right. It is less than R, so it's going to go to the left of R. B, left of M, left of F, and I would be putting in B. So I just made a simple binary search tree. Okay, it's a binary tree. Every parent only has 2 children or 1 child or no children, but it's going to help me to be able to search. So if I said, is T in here? I'm either going to find it or I'm going to hit null. T, does it match M? No. It's greater than. Boom. Does it match R? No. It's greater than. Boom. Uh-oh, that's null. I'm done. I couldn't find it. It only took me 2 moves to see if I could find that instead of going through the entire list. So I have a note here that says size math, and we're going to start talking about levels. I have level. So in some books, they call this level 0, this level 1, this level 2. I prefer to call this level 1, this level 2, and this level 3. So if I have one level, right, and I start looking at my levels and I have 1, how many values can I store? Just 1, right? Just 1. If I have 2 levels, how many values could I store?
2.
Well, I got this original 1, and then the second level is 2, like you said. But what will be the total number of values I could store?
3.
Yeah, 3. If I went down to 3 levels, how many values would I be able to store?
7.
7. So all of a sudden I'm thinking pre-calc. I'm thinking I know what the next number is going to be. It better be what?
15.
I get a 15. How did you get 15?
2 times the level plus 1.
Yeah. Some people might go, oh, wait, 2, 4, 6, it's 13. No, that's actually not it. Okay, that would have been a good guess. But if I take a look at this, now I start to see the pattern. 2, 4, 8. So the next level, I would be adding 16 values. And if I said level N, you would tell me how many values, if I had N levels, could I store?
Two N plus 1.
2N plus 1. That's a good guess, but no.
N squared minus 1.
Say again,
Oh,
Matthew?
no. Nope. Never mind.
No, never mind.
N squared minus 1 doesn't work.
N squared minus 1 doesn't work. Okay. Remember, this is all binary. This is base 2. I just gave you a gigantic hint.
2
Wait,
to
did
the
we-
n minus 1.
Yeah, did we
Yeah,
say
2
that?
to the n minus 1. Okay. 2 to the n minus 1. So at the 5th level, you know, I'm able to store 2 to the 5th power minus, I'm able to store 31 and only take 5 moves to see if it's in there or not. Okay. So this idea of binary tree, it's not going away the rest of the semester. And again, we had to learn linked list, you know, and then doubly linked list. And so we have this nice progression going. So I'm going to take a look at some numbers, and I'm going to put down 5, 8, 3, 4, 12, and 9. And I'm going to build a binary tree, and I'm not going to use pencil. I'm going to go to marker so it shows up better. I'd like to build a binary tree. This is actually going to be a binary search tree. So that means I'm going to put them in that sorted order like I did just a minute ago. A binary search tree. Luckily, these numbers aren't 1, 2, 3, 4, 5, 6, 7, because I'd have a node 1 and then go down to 2, 3, 4, 5, 6, 7. It would be quite the distorted looking binary search tree. That may happen. And in a couple of weeks, we're going to take a look at ways to make sure that doesn't happen. Okay, so I'm going to build a binary search tree. I'm going to start with 5. My advice is if you're drawing these at home, make sure you go wide. I have an 8. Next up is 3. Coming out of here would be 2. Coming out of here would be 2. Here goes 4. Here's a 12. Here's a 9. Okay. This guy would be a null. Out of here, I'd have a null. Out of here, I'd have a null. A null. A null. A null. And a null. I'd have a root pointer. Okay. Levels. I think there's 4 levels. Leaves. How many leaves do we have?
2.
2. 4 or 9 would be leaves. Okay, they point to double ones. All right, so now that I have a new data type, like we've been learning with stacks and with queues and all of these other things, I start to think about, okay, I have a new data type. I'm taking a look at insert. I'm thinking about delete. I'm thinking about traversing. You know, stuff like is empty. Well, I would just check root. Okay. If root points to null, that means it's empty. So I could just say if not root or something along those lines. Is full. It'll never be full. So first thing we're going to take a look at is this guy, traversing. Traversing with a doubly linked list or a regular linked list was I start to the left and move to the right. So I could hit all of the values. Well, when we do traversing here, we're going to be taking a look at 3 different types of traversals. We're going to take a look at one called prefix, one called infix, and one called postfix. Some of you had 230 already with me, and you've seen these 3 terms and you've done a bunch of work with them. But prefix, infix, and postfix. Well, in order to get this started, I'm going to make a diagram and I'm going to call this the node, this the left, and this the right. All right. So if I took a look at a simple math expression, A plus B, and I made a binary tree out of it, it would look something like so. If I made a binary tree out of it, it would look like A plus B kind of deal. All right, so when I'm dealing with prefix, that means the operator comes first. Infix, that's what we normally work with. And postfix means the operator comes last. So prefix means the operator's first. So if I was to think about prefix, I would go with this kind of rotation, plus A, B, plus A and B. It's called prefix notation. Infix, we know that to be A plus B, which means postfix, which is also called Polish notation, would be written AB plus. So we've covered this already, right?
Yes.
Peter's shaking his head. Yes, luckily I can see him. We've covered this a little bit. We've gone into all of these. We had we transferred it over from infix to postfix. We had on the test where we did a push, a pop, and so on. Well, we're going to follow the same idea here, but now instead of looking at this guy, I want to look at this guy. And when I look at my binary tree, my node is going to come first. And again, the left and the right are always going to be in the same order. This time, the node is in the middle. And finally, the node is on the left. All righty, good. So if I took a look at this tree up above. And I said, can that be written in prefix? Again, the prefix was the node was first, then the left, and then the right. So if I want to write this in prefix order, this is one of the three ways that we can take a look at, traverse through this binary tree to take a look at everything that's in it. So I'm going to go node. I'm going to go 5. Can you finish it for me?
3,
3,
8,
nope,
or 4,
4, go ahead.
so then 8,
8,
12,
yeah,
9.
thanks, Peter. So let's see what I did. I went node, good. I moved to the left. I'm at a node, good. I moved to the left. Nope, now I go back. I move to the right, done. Now I go back, back. So I took care of the node, I took care of its left, I moved to the right. When I moved to the right, I hit a node, 8. I looked at its left, no, I looked at its right, boom, I hit a node. Look to its left, boom, I hit a node. Checked left, no, checked right, no, return. Check right. Infix. This time the node is in the middle. So let's see, I started 5. I don't want the node, I move to the left. I'm at 3. I don't want the node, I move to the left. There's nothing there, so I come back to the node, I get 3. Now that I'm at the node, I go right. I hit a 4. That's a node. Does it have a left? No. Do I do the node? Yes. Does it have a right? No. So now I'm going to traverse my way back up. And finally, I hit the node. Now I do the right. I check the left, nothing. I do the node. I move to the right. I check the left, yes. Check to its left, nothing. Check to its right, nothing. Up to 12. What happens with infix? When I traverse a binary search tree, what does infix, what better infix have as a result?
From least to greatest.
Right, sorted in ascending order. Good. All right, finally postfix. This time I do the left, the right, and then back to the node. Give it a whirl, baby. Oh, sorry.
Started 4,
I hear a 4. Keep going. I'm not going to stop you.
3, 9, 12, 8, 5.
First thing, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Okay. I have 6 of them. I have them all. Matthew shook his head. Yes, he likes it as well. See, I went left. No left. I go right. Check its left. No left. Check its right. No right. Boom. I print out the node. Then I go back. I took care of that guy's left. I took care of that guy's right. Boom. I print out the node. I go back. I took care of this guy's left. So now I'm looking at 5's right subtree. I come to 8. I check its left, nothing. So I check his right, boom. I come to here. I check his left, boom. I come to 9. Check the left, nothing. Check the right, nothing. Now I hit the node. Go back up. I just did 12's left. I need to check 12's right. It's done. Boom. I hit the node. I go back up to 8. I took care of the left. I took care of the right. Boom. I display the node. Go back up to this parent. I took care of the left. I took care of the right. Boom. Now I do 5. Nobody wanted to play along with my boom. Fine. See if I can. Threw it at the dog. No, I didn't throw it at the dog. Traversing. I have, in fact, 3 ways to traverse. Insert. Well, a moment ago, we just took a look as we build it with insert. We kept moving with the insert by checking. Is it less than? Is it greater than? And I moved along and put it where I needed to put it. Well, let's take a look at delete. All right, so first thing is, if I said delete, you would give me test data, right? What might I want to delete? Well, I might want to delete the 15.
15.
Yeah, the 15. I might want to delete. So that would be 15 is what head points to. Oh yeah, delete. I'd have to check to see if it's empty first, because we always know that. What the head points to would be one situation, right? So head points to, how about a node with one child, a node with 2 childs, a node with here's a node with 2 children. Here's a node with 1 child. Here's a node with no children. And of course, we'd have the ever popular not found. Kind of a complete list. Hopefully, I'm training you to start thinking this way as soon as it comes up with doing one of these functions. So if I have a new data type and I say, oh, I'd like you to create a function to blah, right away you're thinking test data. What all would I like to delete? Well, let's take a look at this first example. And what if I decided I wanted to delete a child with 1 node, or a child with a node with 1 child, not a child with 1 node. I'm backwards. Okay, I want to delete this. Well, that's not so bad, because I could just take the 15, its pointer, and assign it to the left pointer, or take this pointer, and if it was a right child, not a left, point it to that one. So deleting 1 child isn't so bad. Deleting this guy that has no children, that's not so bad. Okay. Deleting 2 children, oh boy, it gets exciting. We'll spend more time with this as we go through the rest of the semester, but this is going to come up a couple of times. So I'd like to delete 7. Okay. And taking a look at my picture, you might be going, oh boy, here we go. Here's how we do it. If I want to delete a child that, or a node, here I go backwards again, a node that has 2 children, the parent will get the value of the right child, okay? The farthest left that points to null will now point to that left child. So if I would have had another node down here, wherever my farthest left node is on this right subtree would now point to the left subtree. Looks easy trying to draw it with arrows. Drawing it with arrows, yeah, I'm just going to go here. I'm going to go to the farthest left, and I'm going to link it up over there. And woohoo, I'm out, done. Casino dealer. In case you're wondering, I went like that in my hand. I have to do that to the dogs when they see me in the kitchen. You know, like, no more treats, I'm out. I hope somebody's enjoying, I'm enjoying myself today. So tuck that away, something that we're going to look at. Hopefully, you're thinking that hopefully I'm not going to put you in into little groups and make you write this, because I'm not. What I do want you to go to D2L. What I want you to do is go to D2L, and you're going to see some programs. Ba-da-ba-ba-ba. We are in chapter 21 of the Gaddis book. Some of you are getting excited because I think it says chapter 20 on D2L. Is that correct?
No.
Okay, good. Ba-da-ba-ba-ba. It says, oh, they do say 21. Well, that's good, because when they changed editions of the book, they switched it around. I would like you to load up int binary tree dot h int binary tree dot cpp and program 21-1, please.
Can you say that one more time?
You see my screen? It's the int binary tree. It's the header file, the implementation file, and 21-1.
Okay.
I don't need to share. I'm going to come back over here, change my camera back to the book. All right, let's see what's going on in my header file first of all. Take a quick walkthrough and see what we can come up with. Let's see, I have my struct. I'm okay with that. I'm calling it left and right. I have root, which is just a pointer to a tree node. Okay, and now I start taking a look at some private functions. I have insert. I have a pointer and I have a point. Okay, I almost wonder what that's all about. All right, hang on to that idea. Whew. Destroy a subtree. Delete a node. Okay, see that? Okay, make deletion. Oh, look at these three. Display, in order, pre-order, and post-order. So they're the three we're going to take a look at first. All right, we have a constructor. The constructor says root gets the value of null pointer, and we're ready to go. We have a destructor. It's going to blow everything up. We're taking a look at our operations, our methods. Insert, search node, remove. Wait a minute. Hold on, Bubbaloo. If I came up here, I have a private function, insert. Down here, I have a public function called insert node. And in a few moments, you're going to see that the user will say insert node and send a value over. Then there's going to be a call to this guy, to this insert. It's what? Line 36 and line 18. They are, oh no, they're not, because this one's called insert node. I thought they were both insert. I was going to say they're both overloaded. Okay, so moving on. We are going to look at 21.1, and 21.1 starts talking about inserting a node. And if I'm looking at the spec file before I get in there, I see insert node. So I have a number coming in. Some of you are going to go, man, whoever wrote this was pretty good. They were pretty clever. Insert node. I come in and bring a value in. I create a temporary node, a pointer to a new node. Okay. What am I doing here? Create a new node and store it. All right. So this is nice. I'm just creating the node. The node, I have the value. I have left and right, both going to null pointer. Again, an option to make that 0. That seems to work better on all versions of Dev C++. Some want null pointer, some want null in all caps. I think my machine doesn't work with null pointer, so I just double click and make them zeros when you submit them to me. All right, so I come in here and I get this, and all of a sudden, I take that new node I just created, and now, do you remember what was in insert in my header file? it was a pointer to a node and a pointer to a node. Well, right now I'm sending in root and the new node. Okay, let's see what's going on down here in insert. Here comes the root. So this first time's through, this is the root, and this is the new node that I just created. And I take a look at if it's greater than, okay, first of all, if it's null pointer, I'm done. I assign it. Null pointer, excuse me, node pointer, that's the one that just came in. So if my root points to null, that means this guy is pointing to null, and I assign it and done. Remember, this is the address of a reference variable. Kind of confusing, okay? And I'm done because it was nothing. If it is less than, if I take the value and compare it to that node's value, if it's less than, check this out. My pointer now gets the left pointer and my new node still goes in. So this is in fact a what? Matthew's lips moved, but I didn't hear it come out.
Recursive.
Yeah, it's a recursive call. And could we do it with a while loop? The answer is yes. It is yes. So again, I'm coming in, and nice job. I'm coming in with root and the pointer to the new node. If root points to null pointer, then I assign root that value. If it's less than, I now recall the function, but this time instead of calling it with root, which was the first one, I'm going to call it with either this left, the pointer that, the pointer will now become this pointer, this line right here, or this pointer. And I'm going to keep repeating that process until I get to insert it. And somebody was a clever son of a gun. And this is one of those cases where I like recursion. People can get into efficiency and the time it takes, and so on and so on. But this is much cleaner. This is always going to be new node. This is going to start out at head and then possibly become left or right, depending on which way I have to move down the tree. Cracking my knuckles. If you run 21-1, you should see we're able to insert several values. 5, 8, 3, 12, 9. Again, if I drew the tree with 5, 8, 3, 12, 9, you would have a visual. Oh, I did it again. You would have a visual. Oh, is that why you picked 5, 8, 3, 12? Drawing this by hand ahead of time is going to help you. That's the third time I crumbled it. All right, so you all ran 21-1 and it worked, but you really didn't get to see much, did you? Because it kind of just worked. All right, going back to the header file, which was over here. Over here, I have search node. I have, up here in the privates, I have display in order, display pre-order, and display post-order. So let's take a look at what they look like. Display in order. Now this is taking recursion to a different type of level, because while one recursion is running, you're calling another recursion, it's calling another recursion, and a whole bunch of recursions are happening at once, and then they all back out of each other. Taking a look at in order has a node. And when I come in, if the node exists, right, I'm going to move left. While that's being called, this is going to keep calling and moving down to the left. When I'm done with all of the left, I start to come back out of my recursion, and then I print that node. And then I do a go down the right kind of idea and check it out. So the orders, what's kind of cool here, it's doing the left, then it prints the node. If I can't go left anymore, because I hit this and I come back out of this line 158, When I come back out on the line 158, I print out the node. Then I try to go down line 160. It's actually really, really clever in my mind of how it works. So if this is in order, what do you think pre-order is going to look like? It's going to swap lines 158 and 159. Because remember, this is left, node, right. Pre-order is node, left, right. So if I come, we start to come in here, it's node, left, pow, right. Get up there, right. What is post order? Left, right, node. And again, this is a little bit hard to wrap your head around how it can be this simple using recursion. But as you can see, once you got one of them working, the other one worked. All right, so if you run 21-2, now after those numbers go in, you should see a display of in order, which we said should be sorted from lowest to highest, pre-order, and post-order. And again, if you said, I'm getting something wrong, first thing I would do is say, okay, make sure you draw the tree, write out your pre-order, in order, and post-order, and see how it matches or doesn't match to what you have here. But you really need to have some test data, some kind of drawing ahead of time to be able to make sure this works. Okay, so that's one purpose for traversing. That traversing was to be able to print them out in these three different orders, which is interesting. It's kind of neat. Next thing that's up is to search a node. And again, what are we doing? We are returning a Boolean true or false. We're bringing a value in to see if it exists. We're going to come in and another little return true, return false kind of idea going on. It's based around while null pointer. Stays in that loop. If I find it, I'm out. If it's less than, null pointer's left gets the value of null pointer, or excuse me, node pointer, and I loop back up. If it's false, I'm done. If it's true, I'm going to keep looking. Again, I come in. If my root in this case points to null, I'm out right away. I return false. If it doesn't, I check its value. If that's not equal, then I jump down, do the else if, and I keep going. Do you notice line 70 kicks me right out of my while loop? So instead of while node pointer and found not equal to true, we use a return to get me out right away. And I believe 21.3 lets you do that to see if a number was in there or not. Anybody write 21.3? When it comes to deleting a node, we know that it's not going to be as easy. Not going to be as easy. Why? Because we had quite a few different situations to take a look at. We're not going to take the time to walk through it, but if you did, you would start to see if it equals null pointer. I can't delete it. I didn't find it. That is empty. Here I check to see if the left or the right equal null. That would be my one child. So I'm looking at here to here was dealing with one child. And I'm looking at the rest of this to deal with two children. And again, that's one of those where, remember I said we go left, young man, and keep going left as far as we can. And then we would reattach that left subtree. So what I had just deleted, that pointer now goes to the right there to the right. And then I get in this loop to go as far left as I can of that right subtree to reattach it.
Could you have done it the other way by going left and then far right subtree and attaching that to the right?
You would have lost your order.
Okay,
Yeah, I know exactly what you're saying, but you would lose, if you then did an infix traversal, it wouldn't be sorted. So if you want it to be a binary search tree, you have to maintain that nonsense to go with it. Okay, you wrote 21.4, or you have 21.4. Take a minute and see what you can do with it. Run it. All good? Any questions? Okay, so I'm going to come back here to this searching tree one, and I see I have in binary tree, search a node. I'm looking to see if the value exists or not. What I'd like you to do is rewrite this using recursion. Going to put you in groups. When you're done, I'll see you in 12 days. But I want you to rewrite this with recursion. Now, remember how the recursive traversals went. They had to have a public call, and then they called a private function that could keep calling itself. So I don't know if you need one function or if you need that second function to make it recursive. Questions? I'm going to end the recording.